Okay, hello everyone. I'm very excited to be here. My name is Griselda Arroyo-Chávez. I'm a PhD student at the Institute of Radio Astronomy and Astrophysics in Mexico, working with Enrique Vázquez Semadeni and with the recent collaboration of James Rooster. And this talk is about my PhD project. It's a numerical study in which we have been trying to figure out how the specific angular momentum or per unit mass evolves and redistributes during the gravitational fragmentation of a molecular cloud. And today we show you how a SPH code like Phantom can help us to understand the angular momentum transfer mechanism in clouds. So just a quick introduction. The problem that we want to solve is the angular momentum problem, which is the apparent loss of a specific angular momentum, little j, as a cloud contracts, such that the fragments, the cores and clumps have a little j several orders of magnitude smaller compared to the parent cloud. How does it look in the observations? Well, if you plot the total specific angular momentum for different structures versus their radius or size, you will get this, where the larger structures at the top right have a value of little j, several orders of magnitude greater compared to the small cores at the bottom. And typically, little j goes as the radius to the 1.5. Are there solutions to this problem? Yes, well, proposed solutions. And all of the solutions, the objective for the solution is the same, is to slow down the cloud's rotation, either with magnetic field in magnetic braking, turbulent with turbulent viscosity, or gravity using gravitational torques. All of these solutions with their own problems. And actually, we all of these are like torques, and we can also write the active torque equation, where if you take the momentum equation for fluids in cross product with the position vector at with respect to some origin, and you integrate over the volume of a fluid parcel, in principle you will get like R cross P, but for fluids you get the equation that governs the evolution of the angular momentum, where the terms on the right hand side represent the active torques on the fluid parcel, and you can see the gravitational, precious gradient, viscous, and magnetic torques. And also the first term that we call as hydrodynamic torques, which includes turbulent viscosity, and these first 10 tend to go unnoticed. So the key question is, what is the relative importance of these torques? Maybe the solution is not just one term, maybe it's a combination, but we want to know what is the most important one. In our previous work, we analyzed a SPH simulation performed with Gadget 2 with these features. It was a simulation about the formation and collapse of molecular clouds in the warm neutral medium, but without a magnetic field and without stellar feedback. And the first thing is that we reproduce very well the observed relation in the JR plot. So here's our numerical sample. We use a clone finding algorithm based on density thresholds. And here, for example, the red line represents the fit to our numerical sample, and the black line it represents the fit into the observational sample that I showed you before. But not only that, because it seems that the observed relation does not require magnetic field at this, at least to recover the slope, which is more or less 1.5. But this is at fixed times. But if we want to know how the angular momentum evolves, then we need to track in time some of these clumps. And to do that, we use two approaches. The first one, we track clumps as Lagrangian structures, which means that we always follow the same set of particles. So we apply our clump finding algorithm and then track the particles from the past unto the future using their ID. And for example, in the first row here, the definition time is on the right. And if we go from the past to the present time, then we see how the particles are getting closer. In the second row here, the definition time is on the left, and as time goes by, you see how some particles in the periphery lower the density, taking away the angular momentum of the cloud, while the rest of the material is able to collapse. And a second one as over densities at all times. So we apply here the algorithm every time step, and here the mass and the particles are not the same. The clump is able to grow in mass and size. And the results in tracking Lagrangian sets, always following the same set of particles. The evolution in the JR plot is that we observe two periods of evolution, an early one with a slope very similar to that in the observations, here represented with the black line, and a late one with little j evolving more or less constant. Here, the definition time is at the end. In the case of tracking, well, this is the real plot, not just the drawing, the real plot. And you see here, for example, in these three clumps, here the evolution is in this time, and you observe this break in the evolutionary tracks. In tracking Lagrangian sets to the future, again, we see how some particles in the periphery lower the density, take away the angular momentum from the cloud, and the rest of the material is able to collapse. And this is very similar to what happened in an accretion disk, where the material that gains angular momentum moves out of the disk, and the material that loses angular momentum move to the center. And this is, for example, how we observe this. So here is the definition time. The density that we use to define it is like in orange color. And as time passes, you see how some particles and particles here in red lower the density, and the rest of the material is able to collapse. And in using the second approach, tracking clumps as over densities at all times, we see how they evolve along the observational relation, again here in the black line. And it's very interesting because the clumps increase their radius and the mass, even though they are collapsing inside. And for example, here's how for these three clumps, here the evolution is from left to right, and is along the observational relation. But okay, this is the paper if you want to see more details. And the conclusion of this on our previous work is that it seems that magnetic field is not needed to reproduce the observed JR relation or the JR scaling. And the big one is that the angular momentum transfer mechanism is essentially one of fragmentation. So we see how a complete Gaia molecular cloud is not collapsing as in a monolithic way, they is fragmented. So the fragments just have a small fraction of the total angular momentum. So if you think in this way, there is no problem. There's no angular momentum problem. But what is the next step? Well, the next step is consider magnetic fields, but here the key question is, if magnetic field is not necessary to recover the observed JR relation, so what is its role? So in Phantom, I tried because I'm not very good at Fortran, but I tried to combine the cluster and the turbulent setup to create two simulations with these features, which are very similar to the we have in Gadget, with 256 parsecs per second, periodic boundaries, and a closed pack arrangement. This density includes self-gravity from sinks and implicit Koyama Inosuka, and we kept the initial forcing of the cluster formation setup. And one of these simulations has a magnetic field of 3 microgauss. To analyze the terms, to analyze the outputs, I use Plonk, and again, to create a numerical sample of clumps, I use this external SPH clump finding algorithm that you can see more details in the reference. And I followed the same methodology as before at fixed time and to track these clumps in time. These are the two simulations, the hydro simulation and the magnetic simulation, almost at the same time at 10 mega years. And the big difference, like by eye, that you can see is the hydro simulation is more fragmented and form more things compared to the magnetic one, which has more filamentary structures and a low zinc formation rate. If you want to see the 3 microgauss, it's a Cartesian, like a regular, not toroidal. Yeah, I think so. I think is it not the closer to the observed one at these densities? I think so. I think so, I'm not sure. But good question. Okay. Almost to compare with the simulation with gadget, which has like almost the same parameters. But let's see. Okay, if you are interested in see all the images for all the snapshots, you can go to this link. And just as a parenthesis, I was trying just to find a way to see the simulation, like the whole box, and in 3D, like a quick view. And I use this was again totally an experiment. I used the K3D in Python, well, in Jupyter, to plot the entire box. And also, if you go to this previous link, you're going to see a video. Yeah. And this is the video. So this is Jupyter. And here I just plot like a cloud point to see the magnetic simulation. This is this color bar is just to control what density you want to see. This is the density in the log density in particles per cubic centimeter. And well, here you have a panel where you can control the opacity, the point size. If you want to see just one component, in this case, the gas of the things, you can add a grid or just take a screenshot. Again, this is K3D, sorry. And I think it could be a way just to see like the big picture in the simulation. Okay, going back to the presentation. And the results are, well, I also define a numerical sample in both simulations. So in the hydro simulation here, you have the JR plot for different structures. And we see again, like hydro simulations tend to be slightly above the observational relation. Here in the black line, this is the fitting, just like the simulation with gadget. But in the magnetic simulation, maybe the slope is slightly different, but the magnitude of the angular momentum represents very well the observed relation. So the question here is maybe the angular momentum is an angular momentum transfer, like an additional angular momentum transfer mechanism to lose the angular momentum. Of course, we track in time some of the clumps, and in the case of tracking Lagrangian sets to the future, we recover the same behavior in both simulation, innermost region collapse, and the outer parts disperse. And in the case of tracking Lagrangian sets from the past, we see how the clump is assembled. In this case, well, in the magnetic simulation, clumps become much filamentary. And we, well, I plotted here the evolution in the JR plots. And just we wanted to see if we recover this break in the evolution in the JR plug. So for example, here in the magnetic simulation for this clump, we recovered this break. So in a period with little j evolving, here not with a similar slope, but in a late period of evolution with little j evolving more or less constant. But the tendency, well, the trend is to get a continued loss of angular momentum in contrast with our previous study. And in the case of the hydro simulation here, we are not sure that what we are getting this in the hydro simulation. And the next step is just perform a statistical study just to see what is the general trend. And well, the conclusions, are the conclusions for our preliminary conclusions using phantom. Magnetic field maybe adds a second order angular momentum transfer mechanism. That maybe this magnetic field inhibit the constant little j stage of the evolution and produces a more filamentary morphology. So the next step is maybe measure the torques that I showed you in the equation directly in the simulation. And what I would like to learn in here is to use MCFOS and to generate my own synthetic observations and how to add stellar feedback. Thank you.
Thank you. Any questions?
So I was wondering about how you got everything started. So you said you'd combine the turbulent setup and the cluster one. Does that mean you've run a box for a bit without gravity and then switched on gravity or something? Or is it just an impulse at the start?
Yeah, it's at since the beginning. I think the gravity is here since the beginning.
So there's forcing for some time, or the forcing goes through the whole simulation?
If it's form sinks.
So the turbulent driving, you said
the turbulent driving is just at the beginning and then left to decay.
So it's decaying turbulence.
Yes, decaying turbulence.
Could you go back to the slides so I can see one of the graphs with the straight line in it?
You say what slide?
Go back further. There. Now I don't understand why you think that it should be a straight line between the lowest member and the top member in the, say, with the blue ones.
Yeah.
It goes over a factor of 100.
Yeah. Yeah, the angular momentum problem arises if you suppose that the Gaia molecular cloud is collapsing in a monolithic way. So at the end, you are going to form just one core. From the entire cloud, you form more like a sphere collapse, and you are going to form just one. And then you say, well, if we have angular momentum conservation, and these clouds conserving angular momentum, and the core, the small core, will have the same angular momentum. But it's not the case. That is not the case. If you consider that these fragments are just a fraction of the total of the full Gaia molecular cloud, then there's no problem.
If you had a plot with another dimension, it might look like this. But because you don't have the dimension, you just see something that's in a plane. So it's almost as if there is some variable which you haven't included.
Yeah.
Which would change it.
Yeah.
And make it flatter if you had that variable.
Actually, in the paper, we propose a generalization for the AR for this dependence that includes I forgot the name. This density includes the density Oh, I forgot it. But this we include another variable to say that is it's constant, like in this plane.
Thank you very much. We are at time limit now. So thanks again for Griselda.